So let's start. Here we have the first question. The sum of total number of stereoisomers including enantiomers present in the following molecule. Here we have total 2 molecules, so we have to consider both the molecules. Now here answer is given actually both 5 or 7. Now how to what is the logic behind it, that we have to understand. So for the first molecule, this is symmetric molecule, okay, and here we have two chiral center, and when we have two chiral center, normally we use this formula 2 to the power n, but if you use this it will be 2 to the power 2, that will lead to 4. But as it is symmetrical structure, so you will find one meso compound for which ultimately it will not be 4 but ultimately it will be 3. Here you can see all the structures. Here this last form is actually meso. If you simply rotate this CC bond, you will find now CH3 will be here and both the OH group will be away from us. Then you will be able to understand why it is meso. But these two are actually chiral. So total 3 stereoisomers including enantiomers possible from this molecule. So 3 is fine. That means we should get 2 or 4 just to match this answer from the second molecule. Now in the second molecule, this is trans decaling system. Now it is fixed, ring flipping is not possible. Now this bond, that is this chiral center, if you consider, suppose if it can be R or it may be S. Now for the other two center, suppose if these two, if I am considering as R and R, and under RR for these two center, NH2 can have R or S, and when both are S, I am just arbitrarily saying, suppose both are S for these two, now also R and S for this second chiral center, it is possible. So that means if you consider from that point of view, you will get total 4. But if you fix these two positions, then only this R and S for this center we have to consider. So in that case it will be 2. So either it is 3 plus 2 or it will be 3 plus 4. So in this way it will be either 5 or 7. Fine. Now same type of question we can also see from 2018. Here also you can see this molecule, it has similarity with the first one. Here also we have two chiral center, but it is symmetrical molecule, so that is why same type of logic we have to apply. That is the logic that we have applied for the first molecule in the previous question, and that is why here answer will be total 3, not 4. Next we have this molecule where we have to find all possible stereoisomers. Now if I draw this molecule in this way, OH, then we have one CC bond, another CC bond, but in this CC bond we have two methyl groups. Now in this case we have to find stereo center. Now this is one stereo center, here we have chiral center, this is another stereo center. Stereo center means where you can have more than one stereoisomer, okay, and this is actually the chiral center. So as there is total 3, not the last double bond, because here we have two similar substitutes. So that is why we have to consider only these 3 and just apply this formula 2 to the power n, that is 2 to the power 3, and we will get the answer which is 8. So 8 will be the correct answer for this question. The correct statement for the following structures. Here we have total 1, 2, 3 structures, and in all these rings you can find total 4 nitrogen, and there is NH bond mentioned. So whether they are having resonance relationship or they are constitutional isomer, that we have to find. Now remember, when it is resonance, there is no bond breaking or making. It is simply that the double bonds, they are changing their positions, or the lone pair or non-bonding electrons, they can take part in resonance with the double bonds. But here bond breaking, that is not present when we are considering resonance. Now here you can see this NH bond and this CH bond, that is present at 1 and 2 position, but in this case it is 1, 2 and then 3, and in the last one we do not have any NH bond, we only have this CH bond. So here the positions of this carbon, hydrogen and NH bonds, if we consider, obviously they are not resonance structure. So this you can easily cancel, and obviously B and C where 1 and 2 resonance, 3 is isomer of 1, 2, but still this part is obviously not correct, and in C option also this part is not correct. So only the last one, that is the relationship between them is they are constitutional isomers. So this will be the correct option. You can also say they are structural isomers, same thing. Correct order of boiling point compounds 1 to 4. First try to recognize the compounds. This is alcohol, alcohol, alcohol. Only the second one is ether. Now obviously alcohols will have higher boiling point, so 2 will be at the last position. Now 2 at last position, that you can get in option C, also in option D. Now in between, that is among 1, 3 and 4, how to choose? Now in 1 we have total 3 carbon. In 3 also we have total, sorry, in 1 we have 4 carbon, here also we have 4 carbon, and in case of 4 we have total 3 carbon. That means here molecular weight, if we consider, for 1 and 3 molecular weight will be higher. So 1 and 3 molecular weight will be higher compared to 4, and that is why in this case boiling point will be high, because when molecular weight is high, van der Waals interaction also increases. Now that means after 2 the next position will be for 4. If you follow that, option C should be the correct. But why 1 is having higher boiling point? It is because in 1 we do not have any branching, but in 3 we have branching, and when there is branching, surface area decreases, which is directly related to van der Waals interaction, and that is why boiling point will also decrease. So when there is branching, boiling point will be less, and that is why 1 should be having higher boiling point compared to 3. So this is the correct option. Achiral stereoisomers are possible. So more than one answer can be correct. Here the first system is basically alene system. These two positions we have hydrogen. Now for alene, in general way we can say, suppose we have substituents like this. Then we have, this bond, I will write it behind the screen. So C, and suppose this is D. Now just consider this side. When A and B, these two are not equal, then we cannot have any plane of symmetry, center of symmetry, that is not possible. Similarly, this side also, when C is not equal to D, that is these two substituents when not same, then also we cannot have any plane of symmetry. Now just for, it is not just for A, B, C, D, even if you have A and B left hand side and also here A and B, then also it is true, because in case of in this question for molecule A and B, here these two substituents methyl and hydrogen, this is also methyl and hydrogen. Now why I am saying for B also, because for B also same type of logic is applicable. Here we have this biphenyl system with the ortho substitution, and these two phenyl ring, they are not in the same plane to avoid steric interaction. So if the left hand side ring is on the plane of the screen, this ring will be perpendicular to it. Okay, and here you can see similar type of groups A, B, and this is B and A. So for these two molecules, I can draw something like this for general. That is, it is not just true for these two molecules, it is true for any substituents where you have A, B both sides. Now when you have this type of axial chirality, whether it is biphenyl system or alene system, plane of symmetry you cannot get, and that is why here achiral stereoisomer, that we will not be able to get. So these two will not be correct. Now what about the third molecule? In the third molecule we have some chiral center, that is fine. But see, in this chiral center, suppose this OH group is above the plane, this is also above the plane, and whatever is the stereochemistry of this middle OH, still you can get plane of symmetry, right? So that is why achiral stereoisomer is possible. And for the last molecule also, when both the methyl groups on the same side, that is Cs. Here I am drawing both the methyl group above the plane. You can also draw it below the plane, but whatever it is Cs. So it is meso, plane of symmetry is present, and that is the reason here also you can get achiral stereoisomer. So C and D, these two should be the correct option. Total number of constitutional isomers possible for trimethyl cyclohexane. So we have to use total 3 methyl groups that must be present in the cyclohexane. Now one by one we will draw. So cyclohexane, if I put all the 3 methyl groups 1, 2, 3 position. 1, 2, 3. This is one possibility. Another possibility is if I am putting it 1, 2 and 4. Then the third possibility is I am putting it 1, 3 and 5. So these are the 3 possibilities. Okay. Where all the 3 methyl groups, they are not in the same carbon. They are on separate carbon. Another that is a second group that is possible. Because in this case, now what we will do, we will put 2 methyl groups on the same carbon. So when you are doing so, now you are left only with 1 carbon that you can put in this 2 position. Then after putting both the methyl in the same carbon, you can put the second one at 3 position, or you can put the second one in the 4th position. So from these types, this is one type, this is as if another type. So total 3 plus 3, you will get total 6. You cannot get anything more than this. 6 will be the correct option. Dihedral or torsional angle in degrees between 2 methyl groups in the most stable conformation of N-butane. So N-butane is this structure. Now in this structure, if we look at this 2, 3, if we consider this 2, 3 bond, and if we look at this from through this bond, we will get something like this. So here you can see all the structures. This is N-butane, and if our I position is somewhere like this, then we can draw the Newman projection. So starting from this, where the methyl groups, they are that is having 0 degree with each other, right? Now if we move one methyl, suppose you are considering the back carbon, that is this carbon, if we are rotating it, now this methyl group, it will come somewhere here. That means we have rotated it 60 degree. Then another 60 degree, that means 120 degree. You will get something like this. In this way, if you move another 60 degree from 120 degree, you will get 180 degree, where both the methyl groups anti to each other. This is called anti-periplanar. Fine. Now further movement of this CH3, you will get this structure, which is same as this one. This is also eclipsed. But we have to find the most stable conformation of N-butane. And from this graph, that is energy we have in the y-axis, you can see the minimum energy that we are getting for this anti-periplanar. And the logic is simple, because both the larger group, methyl group, that is anti to each other. So that is why this will be the most stable. And when they are anti to each other, the angle between these two, it is 180 degree. So that is why here the answer will be 180 degree. Next question. Degree of unsaturation, that is double bond equivalent, we have to find for this formula. Now the formula that we use to calculate degree of unsaturation or double bond equivalent is this. Here 2C, that means total number of carbon, you have to multiply it with 2. Then we have plus 2 plus N, that means if there is any presence of nitrogen in the formula, that we have to mention. Suppose you have 1 nitrogen, so simply put 1 in this formula. Then total number of hydrogen, you will always have some hydrogen. So you will you have to put it here. And X, X means halogen. Now in our formula, we have oxygen, but whether oxygen present or not, that is not mentioned in this formula. So what we will do, 2 into C, that means 2 into 14, total number of carbon 14, then 2, then nitrogen 0, hydrogen 12, there is no halogen 0. So what we are getting? We are getting 28 plus 2, 3012 divided by 2. So it will be 18, that means it will be 9. So this is the degree of unsaturation. Next question. Diastereomeric pair among the following options is or are. So more than one answer can be correct. Now the first one, it is basically E or Z, right? Now that is also considered under diastereomer, because diastereomer, if you consider the broader definition, that is those optical isomers where you do not have any mirror image relationship, or if you apply that formula, obviously geometrical isomers are, if you apply that explanation, then GI or geometrical isomers, that is also under this diastereomer, right? Here this pH and Me, and it is not changed here, but the position of ethyl and hydrogen, that is changed. That means these two GI, that is also will be considered as diastereomer. So this should be considered as answer. Now the next one, that is B. Here if we look at the chiral centers, methyl above the plane, tertiary butyl below the plane, this is still intact. But see, only here Br, it is below the plane in the first case, above the plane in the second case. Now diastereomer, another way we explain it, that when some of the stereoisomers are changed and some stereoisomers are still intact, then also they are diastereomer. So here only this one it is changed, but the other two they are not changed, right? So that is why this will also be diastereomer. And what about the third one? In third one, OH and Br both are now above the plane. Fine. And if you rotate this molecule out of the plane, you will basically get the mirror image of this molecule, where OH and Br, it will come to this side and they will be below the plane if you simply rotate it out of the plane. So these two are actually enantiomer, not diastereomers, because both the chiral centers, the position of OH and Br, now it is changed. What about the D? So this should not be considered. What about D? In case of D, here we have these two molecules in chair form, and you don't have to do anything, just look at this. This CH2OH, here it is equatorial, right? This is also equatorial. Now this OH is equatorial, this is equatorial, but this OH, here it is axial, here it is equatorial. That means for these two there is no change, but these two, this OH, that is change. So again the same logic that we have applied for molecule B, that is for the pair B, and that is why correct will be, answers will be A, B and D. Number of GOC-butane interaction in the following compound. So GOC interaction, that question arises when you have two groups or atoms and their angle is starting from 0 up to 180 degree. So if the angle is in this range, so mostly GOC is considered for 60 degree angle. And why it is called GOC-butane? Because in butane we have just solved one problem related to butane, and there you have seen one configuration where the two methyl groups, they are 60 degree to each other. So that is actually the isomer or conformation where GOC interaction is observed. Now same type of interaction is also observed in cyclohexane 1,2-dimethyl substituted. 1,2-dimethyl substituted cyclohexane also, same type of interaction you can observe. So that is why it is asked in this way, that the number of GOC-butane interaction in the following compound, because just like butane, here also GOC interaction is possible. So look at this picture. This is basically in butane, and here the angle, dihedral angle between these two, it is 60 degree, and here we have GOC interaction. Now same type of interaction you will also see in case of this 1,2-dimethyl. Now this form is cis because this is axial, this is equatorial, this is cis, and here at 1 and 2 position, sorry, 1, 2, this is 3, this is 4, this is 5. So at 5 hydrogen and 3 position, these two hydrogen, you will also have some 1,3 diaxial interaction, and that is also considered under GOC-butane. The interaction between these two, that you can easily understand, which is just like this, but this 1,3 diaxial interaction with the two hydrogen at position 3 and 5, that will also be considered under GOC-butane. So total how many? Total it will be 3. Now to actually understand this 1,3 diaxial with these two hydrogen, you can also consider the Newman. So in this Newman, basically this CC bond you have to look. So if this is 1 and 2, now this is back carbon, this is number 1, this is front carbon number 2, this is actually in our case one more methyl, and then this is number 3, this is number 4 carbon, this one, and the back carbon is number 5. With this back carbon, this is number 5 hydrogen, and this is number 6. Now you can compare these two structures in Newman and in chair form. This is the interaction with this 1, 3 and 5 hydrogen. Here also you can see the interaction in Newman. So this is very easily you can understand. But this 5 position hydrogen, there will be another GOC interaction. So the angle between these two, this is 60 degree, and if you consider this bond, and this bond, that is also actually 60 degree. Okay, so in Newman also these two are the 1,3 diaxial interaction, and this is between two methyl groups. So total 3. So answer will be here 3. And for extra information, I would like to mention, suppose instead of cis, if trans is given, then what should be the answer? So in case of trans, as we know, when it is 1,2 substitution and trans, it will be either axial axial or it will be both equatorial equatorial. Now if you consider the axial axial form of trans, you will see there will be this 3 and 5 hydrogen 1,3 diaxial interaction with this methyl, and for the other axial methyl also with respect to this methyl, now these two hydrogens are also at 3 and 5. So total 4 1,3 diaxial interaction is possible in AA form. What about EE form? In EE form, there is only GOC interaction between two methyl groups, but there is no GOC interaction with, that is no 1,3 diaxial interaction. Fine. So here we have only one GOC interaction, and here total 4. So this is for trans. And in our case, the answer, that is in our case it is cis, and the answer is total 3. Among dimethyl cyclohexanes, so all these 4 molecules are dimethyl. It is true their positions are different. A and B, 1,2 substitution, we have cis and trans. And in case of C, 1,3 position. In case of D, it is 1,4. Now, which one can be obtained in enantiomer pure form? That means it should be chiral, and the other 3, there should be some symmetry element present, so that is why they should not be considered as that is enantiomer is not possible, right? Now all this chair form, if you simply consider in normal cyclohexane, you can reach the correct answer. So why I am saying so? So this is basically A. It is trans, because when it is trans, both are either equatorial EE or AA. So here it is trans. Now for B, it is basically cis, where this is axial, this is equatorial. This is C at 1 and 3 position. Now at 1, 3 position, when it is cis, basically both are equatorial or both are axial. So this is also cis. And in case of 1, 4 substitution, when it is trans, then it is EE or AA. So this is basically trans. Now in this 4 normal cyclohexane, we have considered not chair. You can find sigma plane here, right? That means A should be the correct option. And if you follow this, you will also reach the correct answer, which is basically option A. But this is not the correct way to reach the answer, though we are reaching correct answer, but the explanation actually not correct. So what is the correct explanation that we should give? See, this is the cis, where one is A, another one is E, as you can see in A molecule. But when there is ring flip, now axial is becoming equatorial and equatorial is becoming axial. From the color you can understand. Now this position, if I am numbering it as 1 and 2, now this will be 1, this will be 2. So what is happening? This cis 1,2 dimethyl cyclohexane, it is achiral, not because, sorry, it is not A, it is molecule B. Sorry. By mistake I have seen it. I have said it. It is for B, that is cis. That is this molecule we are talking about. In the normal cyclohexane form, it seems there is some sigma plane, but actually this is not the correct way for which you are considering this molecule achiral. This is achiral because, not because there is some plane of symmetry POS, but the actual reason is it consists of 2 enantiomeric conformations. These 2 are enantiomeric conformations. You can find the mirror image relationship, where these 2 methyls, from the color also you can understand, axial is becoming equatorial, equatorial is becoming axial. So these 2 enantiomeric conformations, they can interconvert rapidly via ring flipping at normal temperature. So you cannot obtain them in enantio pure form. There will be mixture, because at normal temperature also ring flipping possible. So this is the actual reason why ultimately this molecule is achiral. It is not because of POS. It is because of this reason. So correct answer is A. Number of compounds having S configuration among the following. So the first one, This is number 1 priority, this is 2 ethyl group, this is 3, and this is 4, which is already away from us. Under this condition, when you are moving 1 to 2 to 3, we are getting S. Now for the next one, it is in fission. This is 1, this is 2, this is 3. So 1 to 2 to 3, it is anti-clockwise. But as the lowest priority, it is in horizontal bond. So ultimately it will be R, not S. Then we have allene. Now if we look at this molecule from this side, if this is our I position, then what will happen? H will be here, methyl is here. And this methyl, it will be left hand side of us, hydrogen will be here. Now how to find RS nomenclature? So first the two groups that are towards us, that is these two, you have to put numbering. So this is first priority, this is second priority. Just consider priority for these two groups. Don't consider all the groups, just these two groups. Next you move behind, and among these two, this will be number 3 and this will be number 4. So when you are moving 1 to 2 to 3, then it is anti-clockwise. So that is why this will also be S. And what about the next one? Though we can already see the answer, but we have to give the explanation. This is number 1, this is number 2, this is number 3. Hydrogen, which is number 4, this is towards us. So 1 to 2 to 3, it is clockwise, but as H is towards us, ultimately it will be S. And the last one, this is 4. Then this side we have this group CH2, then CC double bond, right? And this side we have CH2, then CH2. Now under this condition, if we consider the movement, that is 1 to 2 to 3, then what we are getting, it is the movement which is clockwise. But ultimately it will be, we should consider it anti-clockwise because H is towards us. So this is also S. So except the second molecule, in all other cases we are getting S configuration, and that is why total number will be 4. 1, 2, 3, 4. Okay. So that's all for this video. If you find it helpful, please like, share and subscribe. I will meet you in the next video. Thank you for your time.